How will we draw it? And so student number 1 comes in and draws them both on wedges. That is great. So this is all your points. So that's all the points. Student number 2 goes ahead and puts them on dashes. That's all your points. Everybody okay? Student 1 and 2 getting all their points. Student number 3 does this. None of the points. Is everybody seeing the difference? Straight lines, not all the points. Straight lines doesn't say anything to me. All right, so it's either both wedges, yes?
But then I think we do it as a normal line and then just wedges or dashes.
That's fine. For the straight line, I'm so terrible. I'm quite lenient with the straight lines. Quite lenient with the straight lines because I'm not very good at drawing. So the straight lines, if you had done this, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, right? And you would have done, she's saying, can I do this? Right, you're wanting to do that. Yeah? I'm gonna accept it even though it's really not drawn correctly. They're both dials. They're both dials. Every time you have a di as a prefix, the name of the alkane changes. If it was pentanol, if you have a diol, then it becomes pentane diol. You must E before you die. So this guy is heptane diol, and you need to let me know where they are. They're on 3 and on 4 diol. Your cyclohexane will be the same thing. It will be cyclohexane 1, 2 diol. But because it's a cis, you want to say it also that it's a cis 1 cyclohexane 1, 2 diol. Everybody okay? All right, let's take a look at number 4. I want you to do the work, but then I do it all. How is that working out? So number 4, I'm going to go back and do my line angle drawing. So there's my line angle drawing. So it's 2 pentene. I'm going to react this in presence of water, and this is acid catalyzed. So how do we describe pentene now? The 2-pentene, how would we describe it? So look at all the many terms that we used in Chem 3, all right? We called it internal. So first of all, we called it internal. We call it disubstituted. We called it unsymmetrical. Was it regio-selected? And not regio. It had no regio-selectivity. Okay, so it had no regio-selectivity. So what is the beginning of the mechanism? Where is the first arrow going from? From the double bond to the hydrogen. And we ended up with 2 intermediates, right? So you could see this like this. So if that hydrogen went to carbon number 2, the carbocation was on 3, or the hydrogen could have gone to carbon number 3, the carbocation was on 2. They were not the same, but they are both considered equal in stability. Since they are not the same, but both equal in stability, they're both called secondary carbocations. Both of them are made. Okay. What's the next step in the mechanism? Who comes next? The water comes first. So the next step, the water is the nucleophile. The water nucleophile attacks that carbocation, looking like this. I'm going to just track one of them. Attacks the carbocation, generating the oxonium ion, right? So you generate the oxonium ion. So this now looks like this, where you would have the O, hydrogen, hydrogen, dot, dot, plus. This guy called the oxonium ion. And the last step, where the water came in and behaved as the base. Okay, just like SN1. Remember SN1? What was the first step in an SN1 reaction? Formation of the carbocation. The halogen had to leave, exactly. So in the formation of the carbocation, the first thing that you needed to do, you needed to break that carbon-halogen bond. Okay, you started polarizing the bond. You ended up breaking the carbon-halogen bond, forming the carbocation. After the carbocation was formed, then the solvent behaved, number one, as the nucleophile, going after the carbocation. And in the second step, the solvent now behaved as the base, going after the hydrogen. So just like SN1, anytime you generate a carbocation, anytime your reaction produces the intermediate of a carbocation, you're back again at SN1 or E1. All right, so the difficult time is to get to the carbocation. Once you're here, then it is all the same. So I'll go after the hydrogen, pair of electrons return, and my product looks like this, where I'll have the OH in here. And you have the H3O plus, right, so you have more of the water and the acid that you need to recover like you started out with. Okay, so when we asked, is everybody okay? Yeah, so when we asked, right, draw all possible, what did I say? Complete the following and do all the products that are formed. In all the products that are formed from this reaction, you're going to have your, this one. So all the products that are formed from here, you will have your alcohol on carbon number 2 and your alcohol on carbon number 3. Do you only produce 2 products from this reaction? Are there only 2 products in this reaction? It's right there. 2 or more? What happens with carbon number 2? You have R and S, so there are 3, all right? So there's R and S on 2. Don't forget chirality. I'm like super big crazy nuts about chirality. So if it's chiral, acknowledge chirality. Remember, biochemists, I mean, that's like a big thing in biochemistry is, you know, some compounds our body recognizes, and they're R, and sometimes they're S, and our bodies just see them as toxic. So we've got to keep an eye on the chirality of things. All right, what happens with number 5? I think number 5 is probably going to be pretty similar to the other ones. Number 5, 1, 2, 3, 4, 5, 6. Like that. And we're reacting this one with HI. This time I got sloppy. I did not even bother to put in a solvent. Did you see that? I didn't even bother with a solvent. Will we be able to immediately know what the product will be there? No? Doesn't matter. If they don't give you a solvent, the assumption is that this is carbocation. So this is ether. All right, so the solvent here is ether. The only time that you can have it going non-Markovnikov or anti is with HBr is the most common, and sometimes with HCl. HI doesn't work with the peroxide story. So your product is gonna be, what would be the name of the product? Can it be 3,3? Okay, the same story. Tri-substituted alkene. This is a tri-substituted alkene, and on symmetrical, there is regioselectivity, right? Regioselectivity, I think you can see that this guy has a hydrogen. So that hydrogen is going to go there. The iodine is going to go here, right? So everybody saw that? So I'll put an iodide over here, that over there. I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that will be your product. How can I name them? Did we name this? I guess we have to name the compounds too, right? We have to name them. 1, 2, 3, 4, 5, 6. So this would have been what? 3-methyl hex 3-ene. And this one over here then will be 3-iodo 3-methyl hexane. One product or more? Or you want to make sure that you write RNS. Okay, you want to make sure that you write RNS. So if you were sloppy like I was, which is okay, right? We're just, supposedly we're reviewing, and all of this we know. Yes? Has anybody, I mean, I'm mostly interested in the other schools. You've seen this before, right? You guys seen this before? Yeah. Okay. And so the most important thing is if you get sloppy like I do in drawing, just go ahead and call it the RNS, and then we're good. You're just acknowledging the fact that you have generated a chiral compound. This is what we really are. We want to see this. If you started with an achiral, this was achiral, and you ended up with a chiral product, that's when we really want you to acknowledge the fact that you have gained chirality. All right, if it was chiral from the beginning and it ended up chiral at the end, we kind of look the other way. But when there is that big difference, then we really, really want to pay attention to it. Okay, let's do number 6. Oh, my favorite. Absolutely my favorite, number 6. It's like, yes. Yeah. That's what's my favorite. I have nothing to do here. Okay. This was called hydrogenation of alkenes. Hydrogenation of alkenes, you just end up with pentane. All you do is add hydrogens all across. This guy, what would be the name for the starting material? Yes. Is everybody there? You've got to give it a number. So I heard 1 pentene is great. Somebody called it the pent. 1-ene is great. Everybody, the important thing is that you have to, right, you have to give it a number because the double bond could have been on carbon 2 and 3 also. All right, I lied. We'll do one more. Oh, the one more is so long. Okay, number 7. Number 7 is an alcohol. The alcohol is on 3. And we're reacting this with concentrated sulfuric acid. So acid and heat. What happened when you have an alcohol and you react it with acid and heat? You dehydrate an alcohol. Very good. You dehydrate an alcohol. The gentleman there was a gentleman that's a Russian chemist, very well known for the dehydration of alcohols. His name is Zaitsev. And Zaitsev says, when dehydrating an alcohol, look to both sides, right? To your immediate neighbor. I look to the left. Oh, and I have 2 hydrogens. I look to the right, and boy, I also have 2 hydrogens. Oh, let there be light. Magic powers. All right, so when you have the same number of hydrogens, right, having the same number of hydrogens, the next thing that you're going to have to look at is if your molecule has symmetry or not. So if you go and you take away that water from there, right, if you were to remove water from there, your alkene is this. If you remove water from there, if you remove water from there, your alkene is that. Is everybody seeing that? Are they the same? No, they're not. So if they're not, both products are going to be formed, and more than likely like in equal amounts. Okay? So you're gonna, when dehydrating an alcohol, you really are looking to both sides. If both sides are equal, and you produce 2 different compounds, needless to say, you're gonna have to draw them both. So let's come up with another example.
What about the cis and trans?
Oh yeah, we have cis and trans on both. So you have 4 actually. Very good point. Is everybody there listening? Not only do you have the constitutional isomers, the 2-hexene or the 3, but you also have E and Z here. You have the cis and trans. So there really are 4 possible products. Thank you so much. Thank you so much. This one I was too ready to go to the next example. There you go. Right? So what happens if you're doing this dehydration and you're over here without paying attention to E and Z here? So for a moment, if we disregard E and Z for a moment, how many products will you generate from here? For a moment. Is everybody seeing? Now when you're looking to the right and to the left, okay, to the left there's only 1 hydrogen. To the right there are 2 hydrogens. Okay, this is when the story with Zaitsev really makes sense. Zaitsev says, when you're dehydrating an alcohol, go to the neighbor that has the least hydrogens on it, the least, because you will generate the most stable alkene. So if you go to the left, like we said there, your alkene will be that, which is a tri-substituted. Had you gone to the right, it would have been a di-substituted, and it's not, it doesn't exist. It's not as stable. Okay? This time, do we have E and Z here? No E and Z because 2 sides are the same. All right, we're done for now. We are taking another 1-hour break, but the steak has been chopped up. Now we really see you